In the previous video, we had the repetition of the one-dimensional derivative, including the product rule and the chain rule. This video will focus on how we can extend the derivative to functions of several variables, here with focus on scalar functions. Assume that we have a function f that depends on the position in space, which we call the position vector r. In 2D, the position vector would consist of the two coordinates x and y, hence it depends on two variables. When we have a scalar function that depends on the position in space, we often talk about a scalar field, as the function can have different values depending on the position in space. Let's add in an example function to illustrate. To demonstrate the derivative, start by selecting one point on the surface. This point will have coordinates x and y. Now we're going to introduce the partial derivative, first with respect to the variable x. Note that instead of the letter d, we use a different symbol for partial derivative. The definition is relatively similar to the derivative we used for the one-dimensional case. We make one step in the x direction and introduce the point f of x plus delta x and y. We can then draw a line between these points to create the slope. And finally, we are going to let delta x goes to 0, which will give us the slope if we move in the x direction. This is the partial derivative with respect to x. Note that the y value remained constant the whole time. Let us do a quick demonstration of how to use the definition for our example function. As a first step, let us calculate the function at the position x plus delta x. Then insert this expression into the definition of the partial derivative. And insert expression for the base position. Place the minus inside the parentheses. Distribute y. And expand this expression. Distribute 4. All these terms will cancel. Divide by delta x. When delta x goes to 0, this one becomes 0. And the final result becomes minus 8x minus y. This is the same expression you would get if you take the derivative of f with respect to x and assume that y is a constant. If I let the point move around, we can see that it will always be the slope in the x direction at a given point. Next up, we are going to define the partial derivative with respect to y. The difference here is that this time we take a step in the y direction instead. Similar to the previous case, we draw a line between the point and the original position, which will give the slope in the y direction. Note that this time the x value is constant. We let the step delta y goes to 0 to obtain the partial derivative with respect to y. We can calculate the value of the partial derivative with respect to y by assuming that x is a constant and then taking the derivative of f with respect to y. Let us again illustrate the partial derivative graphically by moving the point around. The blue line is the slope in the x direction and the purple line is the slope in the y direction. As our next step, we can introduce the gradient which is written as nabla f. We get the gradient by setting the partial derivative with respect to x as x-coordinate and the partial derivative with respect to y as y-coordinate. Hence, the gradient becomes a vector. For our example, we can say that the gradient of f represents the slope of the surface in each direction. Similar to the ordinary derivative, we can once again talk about the operator nabla, which acts on the function f. We see that it is the operator that adds the unit vectors x hat and y hat. As the function f is a scalar field, the gradient will now become a vector field, as does the direction that varies with position. To visualize the gradient, plot an arrow plot of the gradient of the function f. The length of the arrow represents the magnitude of the vector field. The direction is the direction of the gradient. We can now let the point move around to illustrate how the slope of the surface relates to the gradient field. We have seen that the partial derivative can give us the slope of derivative in the x and y directions. But what about the slope in an arbitrary direction s? First, let us define delta s as delta x x hat plus delta y y hat. The values of delta x and delta y determines the direction of s hat. We could also write this as delta s s hat. The direction s hat would then be given by delta x x hat plus delta y y hat over delta s. Where the length delta s is the length of the vector, which we calculate by the Pythagorean theorem. Now, we are ready to calculate the slope if we were to move in the s direction as the partial derivative with respect to the vector s. Note, we are abusing the notation a bit here, as we are actually not dividing with the vector. We only use the vector notation on s to indicate in which direction we take the derivative. Using a similar definition as before, we take one step in the direction delta s, then check the slope of the curve we get when we draw a line from this point to our base point. As usual, we let the distance delta x go to 0 to get the derivative. Now the question is, how do we calculate this in practice? Start by changing notation to write out the x and y coordinates. Now we're going to create an approximation for the partial derivative in the same way as we did in the 1D case. Since delta y will go to 0, we can add the delta y to this expression without changing the results. Remember, the only time adding delta y will make a difference is when we divide by delta y as well, as that produces a 0 over 0 expression that will have a limit. Next, we can drop the limit and write it as an approximation. Then we can multiply with delta x, and finally move the last term to the left-hand side. Now we have our approximation. Insert it into the expression for the partial derivative in the direction of s. Let's repeat the whole step again, but without adding an additional delta y. We can then insert this approximation as the second term in our partial derivative expression. We can remove the f of x and y terms. And we have an expression for how to calculate the partial derivative in the direction of s. Now let us try the following. Take the dot product between the unit vector s hat and the gradient of f. Insert expressions for s hat and the gradient. and carry out the dot product. Note that this is the same expression as the expression for the partial derivative with respect to s. This means that the partial derivative with respect to direction s is s hat dot the gradient. Taking a partial derivative in the direction is called the directional derivative. To show it as a graphical representation, start by adding the direction we want the derivative in and its unit vector s hat. Then add the gradient vector, which gives the partial derivative of the function. Now we can do a projection of the gradient on the direction we want the derivative for, using the dot product. The length of the projection is s hat dot nabla f, which is the value we are looking for. Therefore, I hope it seems logical to you that if we want the derivative in one direction, we can simply project the gradient onto that direction. Moving on to an application, let us start by drawing contour lines for the figure to the left. A contour line is a curve where the value of the function is constant along the entire curve. This is very common for maps, where the elevation is drawn as contour lines. One will get an indication of the slope or derivative by checking the distance between the contour lines. If the lines are close to each other, expect a large slope. Let us try and take the directional derivative along one of these curves. As the function value is constant along the curve, the derivative clearly has to be 0. This means that the contour lines are perpendicular to the gradient of the function. We can therefore add the gradient in the figure. We can say that gradient will be the normal direction of the contour lines. Another useful visualization technique is field lines, which are lines that follow the direction of the vectors. These field lines will always be perpendicular to the contour lines. If we animate them, they will show our motion if we move in the direction of the vector field. Now we can extend this result to calculate the normal vector of our surface to the left. The first thing we can do is to change the interpretation of the surface to an actual surface in 3D space. We can do this by including the z coordinate and setting its value to f of x and y. This means that z is f of x and y, or we could write z minus f of x and y is 0. Call the function z minus f g. On the surface, we know that g is 0, hence g is a constant on the surface, similar to what we had for the contour lines. Now we can take the gradient of g. Insert expression for g. When we take the partial derivatives of x and y, remember that z should be considered a constant. Hence, the partial derivative with respect to x is minus df dx. Similarly, the partial derivative with respect to y is minus df dy. And the partial derivative with respect to z will be the derivative of z, which is 1. As g is constant on the surface, any vector parallel to the surface will give 0 when we take the directional derivative with it. Hence, the gradient is perpendicular to the surface, which means that it is the normal direction. There is an alternative way to get the normal vector. Start by defining the vector v as the partial derivative of the vector r with respect to the coordinate x. When we apply the partial derivative to a vector, we simply apply the derivative to each coordinate separately. dx will be 1. dy dx is 0 as y is considered a constant when taking the partial derivative with respect to x. This will create a vector that will be parallel to the surface. We realize that it's parallel as the f dx is the slope, hence the derivative gives a vector tangent to the surface. We can create a second vector w by taking a partial derivative of r with respect to y. Repeating the same steps, dx dy is 0 and dy is 1. And we get our second parallel vector. If we have two vectors and want to create a vector that is perpendicular to both, we can use the cross product between them. When evaluated, this becomes minus the f dx, minus the f dy, and 1, which actually is the same vector as our gradient. All we need to do to get the normal vector n hat will be to normalize these by dividing by its length. Moving on, let us mention the derivative rules we talked about in the one-dimensional video. The first one is the product rule. Note that the derivation for the product rule works in the same way for the partial derivative as the 1D version. This means that the product rule can be applied for both the partial derivative with respect to x and with respect to y. Since it works for each direction in the gradient, the product rule will apply for the entire gradient as well. The situation for the quotient rule is about the same. It still holds for the partial derivative, and therefore we can write it for the gradient as well. Before we go to chain rule, let us first mention what happens in the case that f is a function of x and y, but y in itself is a function of x. If I take the definition of the partial derivative and include that y is a function of x, we would still write y of x everywhere y appears, which will consider y a constant when we apply the definition. Hence, the partial derivative will not change when we add that y is a function of x. When we calculate the total derivative, we would change y in the first term to evaluate at the position x plus delta x. The total derivative is written with the letter d, just as we did in the 1D case. In this case, we would have the chain rule that the f dx is the partial derivative of f with respect to x plus the partial derivative of f with respect to y times dy dx. This is the chain rule between total and partial derivatives. Let us demonstrate this concept with an example. Assume that a graph represents a hill and we are going to take a walk on this hill. The height of the hill z0 is described with a function that depends on the coordinates x0 and y0. Call our position on the hill r, which is a function of the time t. We can write it as x of t and y of t. To get our altitude, start from the height of the hill as a function of x and y coordinates. Then insert our coordinates as x and y to this function. We now have that our altitude is f of x and y, where both x and y are functions of time. If we add our position to the figure, we can see that our altitude will depend on our position on the hill. What we want to calculate is how our altitude changes, which will be the total derivative of our altitude. Start by introducing our velocity v as the total derivative with the r dt. Let us consider a small change in our position delta s. This change in position should be given by our velocity and the time delta t it took to make this small change. The velocity vector can be written as the speed v times the direction s hat. By rearranging, we get that delta s over delta t is the velocity v s hat. We could also write it for the speed v. Let's introduce the total derivative with respect to time. We can multiply and divide by delta s. Let delta s and delta t swap places. The position vector at time t plus delta t should be the original position plus our change in position, delta s. This expression is the directional derivative. Delta s over delta t is the speed. V times s hat is the vector v. And we get that the total time derivative of f is our velocity dot nabla f. If we type out this dot product, we will recover the chain rule that we saw in the previous case. To make the example more flexible, let us change from hill to let the figure represent the temperature. With the temperature, we can also consider that the temperature could change with time. Instead of our altitude, we now consider the temperature at our current position. We also need to add in the partial derivative with respect to time, as the function f now is time dependent. Now we have our final expression for the total derivative with respect to time, and we can visually illustrate this. Start by looking at our partial derivative with respect to time. This represents a change in the temperature in the room. Next is a partial derivative with respect to x multiplied by the velocity in the x direction. This term represents how the temperature we experience changes as we move in the x direction. And finally, the y term represents the change in temperature we experience by moving in the y direction. The difference between partial and total derivative is therefore that the partial derivative only considers changes in temperature in the room, while the total derivative also considers that the temperature changes if we move to a different position within the room. Once again, we could consider d dt plus v dot nabla an operator that acts on the function f. In fluid mechanics, we call this the material derivative, and it will appear in several important equations. Let us try and apply the same to a vector field, here, called the vector field B of R and T. If we use Cartesian coordinates, we can simply apply this operation to each coordinate separately. Be aware though that this is only for Cartesian coordinates, otherwise it's more complicated. We can simply change the scalar equation to a vector equation instead. Let us plot an arrow plot for a vector field. In this case, the vector field B is the gradient of f. Let's do a visualization again, now showing the vector field B in the arrow plot. If we start by looking at the partial derivative term, this still represents that the field itself changes with time. As B is a vector, our time derivative is also a vector. If we move to our x derivative term, this means that we would be changing our position in the x direction. This will cause changes in the direction and magnitude of the vector at our position. Finally, the y derivative term means that we are moving in the y direction. I will end it with a more fluid mechanics related example. Replace the vector b with the velocity v. This term will appear in Navier-Stokes equations which are the most fundamental equations for fluid mechanics. In this example, we will look at a pipe with a contraction. We can also add in feed lines or streamlines, as are called here, which indicate the direction of the flow. Let us look at the term v times nabla v, which is the flow velocity multiplied by the directional derivative. In fluid mechanics, this is called convective acceleration and will describe how the particles accelerate due to spatial variations in the velocity field. Start by looking at the white segment of the pipe to the left. We can see from the arrows that the flow velocity is constant. This means that the gradient of v is 0, hence convective acceleration term is 0. In the contraction, we see that the particles passing through it will accelerate as the flow velocity increases with the x-coordinate. Hence, this term should be positive. Finally, at the narrow part, the flow velocity is constant again. Hence, no gradient and acceleration is 0. This is easier to see if we add the particles. They start moving at a constant speed. When they reach the contraction, they accelerate and then continue with constant speed after. Let's also look at the partial derivative term, which in fluid mechanics is called local acceleration. This term represents changes in the vector field, meaning that the whole flow in the pipe slows down or accelerates. This would give an acceleration to each individual particle. Hence, we saw that we had two ways of accelerating the particles. One is by changing the flow in the whole pipe, and the other was due to change in the velocity field when the flow reached the contraction. This will be the final example for this video. In the next video, we'll talk more about vector fields. We'll focus on the divergence and the curl. Thank you.